Hello everyone, welcome to Practical Math B. We are in week 9 learning about productivity and graphing linear and quadratic functions. Here's our essential question for the week. What is the relationship between the number of workers and amount of a good or service produced? Our objectives, we're going to be defining the marginal physical product and the law of diminishing marginal returns. We're going to explain why the relationship between labor and output is quadratic, all else being constant, and not linear. We're going to explain the features of a linear function and a quadratic function given a table of data. And we're going to sketch a graph, and we're going to use our Desmos calculator to graph a quadratic function and a linear function given a description of the function. All right, so take notes, pause this video at any time. There's also week 9 text to read more about these topics. But use this video as a resource while working on the lesson quiz and any other assignments for the week. Let me know if you have any questions. Please email me, call, or text. I'd love to help work with you. All right, so you're growing a business. What obstacles are there to a business growing? You may start off small, but usually people want to get bigger. Let's watch a video about Mo's bows to get a sense of what it takes to grow a business.
In Season 5, Dame and John offered to mentor Mosiah Bridges, an 11-year-old fashion designer with a handmade bow tie business.
In 1989, I was offered $10,000 for 40% of my company. I'm glad I didn't take that money. I strongly suggest you don't take on investors at this time.
Let's see what they're up to now.
I didn't get a deal on Shark Tank, but I got something much better.
Tramika, Mo, how you doing? Bringing in for a family hug?
A mentorship with my fashion idol, Dame and John.
This factory is going to help get Mo's bows all around the world.
Before Shark Tank, we only had $55,000 in sales. Now, 7 months after Shark Tank, we've reached almost $200,000 in sales. We need a manufacturer more than ever, and we knew Damon could help us out.
This is Robert from Robert Stewart.
Hey, Mo, how are you?
I found Mo the perfect manufacturer, Robert Stewart, a manufacturer that's been hand-making ties for 100 years. This is good old American manufacturing.
Good old made in the USA.
That's right.
Being made by hand and being made in America are very important to me. You want people to know that you stand behind your tie, and it helps keep jobs in the economy.
This is what you do at home. Now, you do it in a factory. We had to find a manufacturer that can meet the demand and stay true to Mo's mission. It's a perfect match. This has been amazing. Thank you for showing us the factory.
Pleasure.
One of the most exciting things that happened to Mo's Bows is the CEO of Neiman Marcus personally reached out to us. She wanted to do a test of Mo's Bows in Neiman Marcus. Neiman Marcus is the gold standard of luxury retail stores. Designers spend all their lives attempting to get here, and Mo has done it at 13 years old. You do well, you could be in every Neiman Marcus in the world.
Seeing my bow ties in Neiman Marcus makes me feel like I arrived. Since coming on Shark Tank, everything has changed in my life.
Now it's my turn, let's do some shopping.
Okay.
I made some amazing deals on Shark Tank, but this mentorship is special to me. I was mentored by great people. I'm trying to pay it forward, and he's making me proud every single day.
So, after the video, where was Mo producing his bow ties before the factory? Well, he was just doing them out of his home by himself, right? Showed him cutting the little bow ties and making them. So why did Mo want to move production to a manufacturer like Robert Stewart? Well, he could only make so many bow ties by himself, right? Only so many resources at his house, only so much space, only so much he can do physically. So going to a manufacturer, having lots of people work on making ties, you can produce a lot more. So what do you predict is the relationship between the number of workers in the manufacturing facility and the number of bow ties produced? Obviously, more workers means more produced, right? But does it get more specific than that? Are there such thing as too little or too many workers? That's what we're going to get into today and use math to help understand. All right, here's an example scenario. Say Mo gets a 100,000 square foot manufacturing plant, and there is space for 10 bow tie making tables and a space to store fabric and a packaging shipping center. What do we predict will happen if they hire the following number of employees? So let's think about this, right? 10 tables, lots of fabric, lots of shipping, all that stuff is able to go on. So let's say if he hires 5 employees, Well, how many ties can produce? Let's say each employee can make 20 ties a day. So maybe they make 100 ties, right? If they go from 5 to 10 employees, maybe they're able to make more ties. Maybe they make 200. I would predict that they would increase, but there's a certain point where they only have 10 tables. They have a packaging shipping center. Some people are going to work there. Some people are going to run and store fabric. But when you get to a lot of people, I don't know if a lot of people sitting around all around the tables is going to really make that much more ties. So you might see it increase, but maybe to a certain point it gets too crowded and all of a sudden we start slowing down a little bit. At least that's might happen, right? We have to think about these things when there's actually too many people to really make and grow the amount of ties produced. Is there a point where there are too many workers? The law of diminishing marginal returns, that's what we're going to deal with today. It describes a phenomenon in economics observed in all short-run production processes when at least one input is fixed. So here we go. As more and more units of a variable input, usually the labor, the number of workers, as we increase the number of workers, are added to the fixed input. The fixed inputs are things that can't change. The additional marginal output associated with each increase in units of the variable will eventually decline. That's just a fancy way of saying, as a business, certain things are fixed and you can't increase that. So say you're a business, you have a warehouse, right? That size is not going to get bigger. We can't just say, well, let's make a warehouse bigger. We're locked into whatever location is rented out. If you're a dance studio, you can't have 2,000 students in your dance studio, right? It's just not big enough. So there's a certain point where you just can't fit anymore. So a studio space, warehouse space, things like that are fixed. We can't get any more. But workers, we can hire more workers, we can hire more things, we can get more supplies, all that stuff. So what happens is successive increases in a variable factor production added to fixed factors of production will result in smaller increases in output. Now, a lot of big words there, so let's watch another little video to help make sense of kind of what this is. This guy explains it really, really well.
Hey Econ students, this is Jacob Clifford. Welcome to ACDC Econ. Today we're going to find out what happens when you keep adding more and more workers and the law of diminishing marginal returns. Guys, seriously, we don't all need to be here right now. In this video, we're looking at the relationship between inputs, the resources to produce things, and outputs, the things that producers make. For example, when a pizza company hires more workers, what happens to the number of pizzas they can produce? Before we jump into it, there's a few details we have to cover. First, keep in mind that there's two types of resources, fixed resources and variable resources. Fixed resources are fixed. They don't change as you produce more, like a pizza oven. If you produce one pizza or 500 pizzas, you still need that one oven. Variable resources do change with the more that you produce. So the more pizzas you make, the more workers, dough, and cheese you need. When it comes to producing things, economists like to differentiate between the short run and the long run. Now, it's not a set amount of time, like 2 weeks. It's more like an idea. A company is in the short run when they have at least one fixed resource. So today, right now, a pizza restaurant is in the short run because they only have one oven. The long run is more about what could potentially happen in the future. So in the long run, all resources are variable. So what if the company had 2 ovens, or 3 ovens, or 10 ovens? The long run also has the idea of economies of scale, which I'll cover in a different video. So in this video, I'm going to talk about production in the short run when there's at least one fixed resource. Okay, here we go. When you hire no workers, you get no output. But when you hire one worker, they have to do everything on their own. They can't specialize. 2 workers can split up the work and produce a whole lot more together than any one of them could on their own. This shows the benefits of specialization, right? 2 heads are better than 1. In this case, 2 hands are better than 1. But specialization has its limits. As you add more and more variable resources, eventually you're going to get less and less additional output. This is the idea of one of the most important concepts in economics, the law of diminishing marginal returns. As you continue to add variable resources to fixed resources, the additional output will eventually decrease. Notice that I said that it will eventually decrease. It can increase because of specialization, but you keep hiring more and more workers, eventually you get less and less output. Here's some made-up numbers to help you understand the concept. Right here, this first column is number of inputs, in this case workers. The second column is the number of output, the pizzas they can produce in 30 minutes. These numbers show the law of diminishing marginal returns, but it's easier to see them by calculating something called the marginal product. That's the additional output generated from hiring one additional worker. Okay, pause the video, see if you can calculate the marginal product on your own. When you're a jet all the way from your first cigarette to your last dying day. The first worker can produce 5 pizzas, so the additional output they make is just those 5 pizzas. But when you hire 2 workers, they can produce 15. So the additional output from the second worker is an additional 10 pizzas. This shows the benefits of specialization. 1 worker can produce 5 pizzas on their own, but 2 workers can more than double that output. 3 workers can produce a total of 20 pizzas, but the additional output produced by that third worker is 5 pizzas. And of course the fourth worker adds an additional 2 pizzas, and the fifth worker adds an additional 0. But now at the 6th worker, the total output actually falls. So the marginal product is -4. Now keep in mind, this is not because the workers are lazy or dumb, it's because of fixed resources. Okay, here's a question. With which worker does the law of diminishing marginal returns set in? I want to be in America. I want to be in America. I have to be in America. Now it's not the 6th worker, it's the 3rd worker. Notice the marginal product has been falling ever since the 3rd worker. That's diminishing returns. It's not when it actually goes negative. That's negative returns, a completely different concept. Actually, there's 3 stages of returns. Right here is stage 1, where the marginal product is increasing because of specialization. Total product is increasing at an increasing rate. Right here is stage 2, because the marginal product is falling because of fixed resources and the law of diminishing marginal returns. Total product is increasing, but at a decreasing rate. Right here is stage 3, and the marginal product is negative, which means the total product is actually falling. This is because the workers are in each other's way and they're fumbling over each other, and there's just way too many cooks in the kitchen.
All right, I feel like you have a good grasp on what the law of diminishing marginal returns is? I hope so. Let's play around with some numbers here. So here we got 2 different manufacturers, manufacturer A and B. We're going to look at if we increase the number of workers, if we go from 1 to 2 all the way to 12, we can see for both manufacturers there's an increase in how many bow ties that they're able to make, right? On first glance, you may say, well, manufacturing B, look at that, they make more, whereas the manufacturing A makes less. But we're going to investigate and play around with some of these numbers and do some math with this. So first of all, let's find the marginal product increase for manufacturer A. What does that mean? Remember, we've done a few lessons now working with this idea of marginal, right? Marginal would be the increase for 1 more. So in other words, if I go from 1 to 2 workers, what's the increase in marginal product there? So from 1 to 2, for that increase of 1 worker, we're going from 18 to 36. That's an increase of 18. That's my marginal product. All right, let's go from 2 to 3. How much do I increase from that? From 36 to 54, that's another 18. And in fact, if we look at all these, we'll really quickly see this is just a pattern of adding 18 over and over and over again. Now, does this seem to fit the law of diminishing marginal returns? For manufacturing A, every time we add a new worker, that 1 more worker makes 18 more bows for the day. And in fact, there's no wavering, there's no difference. Hire another worker, make another 18 more bows. No. That's definitely not an example of the law of diminishing marginal returns. This is kind of a fantasy world, right? Sort of a make-believe, like if we just hire 1, this is what they'll add. But it doesn't account into, do we have the space? Do we have the resources? Do we have the capacity to have this many people working to make that? So, nope, this would not seem to fit the law of diminishing marginal returns. Well, let's compare that with manufacturer B. What do we got going on here? So let's find the marginal product. So from 1 to 2, what's happening with B? Well, they're going from 18 to 50. That's an increase of 32. From 2 to 3, what's happening there? Well, if we're going from 50 to 92, well, that's an increase of 42. Okay, so they definitely got a little bit more. Hiring 3 workers definitely is better than 2 workers. All right, let's go from 3 to 4. What's the marginal product there? Well, from 92 to 40, that's 48. So they're definitely grooving. In the video, they talked about specialization, right? Having 4 people, they can split up what tasks they do and get things done a lot faster. Let's do 4 to 5. They're going 140 to 190. That's an increase of 50. Sweet, I like it. So from 5 to 6, where's that going on? Well, back down to 48. So still a pretty big increase, but we seem like we kind of peaked. Let's just go all the way. If we keep going all the way, we've got 42, 32, 18, 0, negative 22, and negative 48. All right, so there we go. Does this seem to fit the law of diminishing marginal returns? Well, we hire people and we seem like our productivity increases, right? We're able to make more with each new hire. But then there's a point where hiring more people isn't becoming efficient anymore. We can still kind of make more hiring that 9th person, but not as much as we did when we made the 8th person. And in fact, there's a point where too many people, things go south, right? We actually make less. Who knows what that means? Maybe one person goes crazy and blows things up, but we're declining in production. But yeah, this is actually a better indicator of the law of diminishing. Diminishing means getting less. For each one more worker, there's a diminishing return in terms of the product that we get. There's a point where we max out, and there's a point where going beyond that doesn't seem to work as well. All right, so let's switch it. There's our data. What we're going to do now is we're going to switch this into using our Desmos calculator. We have some data. We can think of this as our X values that are changing. And we can think of these as 2 different sets of Y values. And we can look at trying to make some equations. We're going to try and make some graphs. And we're going to try and think about what does our math help us in terms of understanding the data that's going on here. All right, so here I am in my Desmos calculator. And if you want to put a table of data, you need to come over here to the little plus sign. We're going to add an item, and we're going to add a table. Now we know we have 12 workers, so I can quickly go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we have 2 sets. I'm going to put a little Y2 here. We could think of this as manufacturer A. I could think of this as manufacturer B. And I could have one table that kind of fits with what we've already filled out, what I've already been working in this example, right? And I've already made these tables, so I'm going to go pull them up here. Let's first look at the total bow ties produced. So here's that first one, right? Remember for manufacturer A, for every one they produced, for every new worker, they made 18 more bow ties. So you can quickly see what's going on with this one, right? It's growing. It's a nice straight line. In fact, if you think of our algebra, when we look at this, we think of a linear function, right? A linear function is a function that goes in a nice straight line, has a constant rate of change. Well, let's go ahead and do some stuff here. I'm going to use our Desmos calculator, and it'll help me find the equation of the line that fits this data. And I'm going to show you how to do that. Keep in mind, we're going to relate this column of Y1 data with this column of X1 data. And I'm going to use it in slope-intercept formula. So remember y equals mx plus b? Well, in my Desmos calculator, I'm going to say y1. It's not exactly equal to, so I use in my keyboard, we go to ABC, and there's this little symbol here that we're going to use to say approximately equal. So it's finding a line of fit. It's not exact. If it was exact, it'd be an equation. This is approximately equal to m, my slope, x1. So now it's relating the 2 variables, the 2 columns of data. But I need my y-intercept plus b. All right, what do we got showing on here? Well, it made a nice blue line that, look at that, goes right through all my points. And what is it telling me now? It's telling me that my m, my value for m, which we know is the slope, is 18. We already figured that out, right? We knew that every worker added 18 more bow ties. I mean, so we can see that here in our math. When my slope is 18, it means it's increasing by 18 for each new worker. My y-intercept of 0 right here, for b is 0, it just means that if I don't have any workers, I'm not going to make any bow ties. So we have our equation. It's y equals 18x plus 0, or just y equals 18x. That's an equation that models this data right here, the amount of bow ties that manufacturer A produces. But we already decided, no, that actually does not realistic. It does not fit this idea of diminishing marginal returns. So now let's play around with y2. What's going on here? Well, the purple lots seem to kind of go up, but then they definitely curve. There's something kind of interesting going on, right? So for curving graphs that look like a U, we've been working on quadratic equations the last 2 weeks. So let's delete this one. And let's put in a quadratic equation that relates y2 with x1 and see what we have going on here. So quadratic equations are ax squared plus bx plus c, right? So I'm going to do y1 is equal to a times, whoops, that's not y1, it's y2 is equal to a times x1 squared plus b times x1 plus c. There's my standard form of a quadratic equation, and it's using my x1 column variable, relating it to my y2 column variable, but it's not showing anything up because I put an equal sign. I need to change that and put in my little squiggle, right, my approximation. Now what do we got? Well, now we made a nice quadratic equation that's attempting to fit itself as best as it can around the purple points, our actual data. Now, it doesn't fit as good as the linear one, right? Well, that's okay. My r squared, all this is telling me is how well it does fit. The closer it is to 1, it's a better fit. The closer to 0 means it is no fit at all. So 0.96 means it fits reasonably well. It's not a bad model. And you can see it kind of follows the trajectory of the purple lines there. But there we go. There's my values for A. It'd be negative 4x squared plus 80x plus negative 91. So now I have a quadratic equation that is fitting my data. So we can use our Desmos calculator to come up with models that seem to fit. And that's what people do. We have data everywhere. We use computers and we try and come up with mathematical models that fit. The linear one fit perfectly. This quadratic one fits okay. Not the greatest, but it fits okay. Now, this is all great, but as a business, what would we see here? From a business standpoint, if I was looking at this equation here, I would think, okay, my idea would be to hire 10 workers. According to my math model, 10 workers would be the most efficient. Or if I just looked at the data, it'd be right around 9 or 10. According to how many I produced, it seems like it gets bigger and gets bigger and bigger, and then right here at 9 and 10, it slows down. And so if I want to make the most, I should go to 330. Now that's great, but it's not the best thing. We want to look at marginal, right? If I hire somebody, I want to know how much of a benefit will it be to hire one more person. So we're going to open up not the total bow ties produced, but now let's look at another graph. Let's look at marginal product. We already found these, but now we're going to look at, we found these values earlier, right? When we did the differences for hiring one more worker. Manufacturing A is not interesting, right? We knew that was 18, so we get this nice flat line, but that's really boring. We're curious about the realistic situation. For manufacturer B, how many employees should they hire based on our marginal returns? Well, you can see it kind of goes up and it decreases. Let's see if we can find a quadratic model for this. So y2 is approximately equal to a times x1 squared plus bx1 plus c. Ooh, this one fits really nicely. Look at that. In fact, r squared is 1, so it's an exact fit. And in this case, looking at marginal returns, it actually would be the most efficient business model to hire 5 people. I'm going to increase and hire at 5. I get the most bang for my buck when I hire that person. Anybody I hire beyond that doesn't make quite as much money as it did before. Or doesn't make quite as many bow ties. So there we go. At 5, that is the most efficient amount of employees that I should have for my business. Not that 9 or 10 that the other graph looked like, right? So that's where marginal returns is really helpful. So now we came up with a quadratic model. We're able to see what the best decision making for our business is. All right, so in conclusion, what did we do? Well, we did some mathematical modeling with our Desmos calculator, right? We came up with linear equations and talked about slope. We came up with quadratic equations when it looked like the data was more quadratic. And what we saw is manufacturer 2 is definitely more realistic when it comes to thinking about how much you can increase production in the short term. Again, this is a difficult thing for business to work through when they want to grow. They often have certain limited resources or things that are fixed or really expensive to increase. And so there's a certain amount of efficiency they can have in terms of increasing other things. Businesses are usually stuck in their building space, or they're stuck with the certain robots and technology they have, or they're stuck if they're pizza place with only one oven. So hiring more workers is not always the best thing. So you want to be able to use math. You want to help figure it out. For businesses that do want to grow, that's where you need investors who can bring in a ton of capital to get past some of the short-term fixed resources and help you kind of grow. Maybe you can buy a bigger space, or you can purchase 3 pizza ovens to make more pizzas. In the meantime, mathematics is important to make sure you are hiring the right amount of workers and running your business the most efficiently. All right, so reviewing what we did, we talked a lot about marginal physical product. Again, how much more do we produce if we increase a worker by 1 more worker? We talked a lot about the law of diminishing marginal returns. Explained why the relationship between labor and output is quadratic. It increases, but then there's a point where too many workers actually causes you to decline. We looked at linear functions and quadratic functions. We did tables, we did equations, we did graphs. We did a lot of graphing with our Desmos calculator. All right, hopefully this was helpful for you to understand the uses and applications of linear and quadratic models. And I look forward to working with you the rest of the week.